is.
All right, there we go. Take it away, sir.
Awesome. Sorry, I'm just trying to move the Zoom tab out of the way. But yeah, I'm
Yeah.
Steven Seeger. I currently work at Marketile as a senior data engineer. Also dabble in the engineering side, whether it's like improving our code base or rethinking our methodology for some of the A/B testing that we do. Um, get involved in that. My background, I have an undergraduate in statistics and a master's in computer science with an emphasis in artificial intelligence. And kind of my interest in big data is being able to process big data very quickly, cheaply, and computationally efficiently. And I think that's like a really interesting kind of segue for statistics because of like statistics is the basis of machine learning. Um, and a lot of people know about like frequentist statistics, but not too much about Bayesian statistics. And I think that's a very interesting field. So yeah, I'll kind of get going with my presentation from here. If you have questions, I don't know how well I'm going to be able to see chat, but just, I don't know, I guess unmute, interrupt me. That's fine. But yeah, so this will be a brief introduction into Bayesian statistics. This is based off of a book called Statistical Rethinking. I've been kind of hosting sessions at my office about Bayesian methodology and Bayesian thinking and statistics as well. And so this is kind of taken from that. Today, kind of the agenda and the goals of this presentation is talk about the golem of frog, small and large worlds, garden of working data, building a model, analyzing the output. And if there's time, we'll hop into potentially extra exercises and like ways of understanding the basics. And our goals are understanding what a statistical golem is, understand what Bayesian statistics are, appreciate what the output of a model, a Bayesian model, truly means, and generate some posterior distributions. So we'll start off with the golem of Prague. The folklore of golems is like they're play robots from Jewish folklore. They're very obedient to whatever they're told to do. And there's a quote: "Its abundance of power is matched by its lack of wisdom." And you can kind of relate this to statistical golems. Scientific models are very powerful tools, but they don't have intent of their own. They carry out calculations very obediently, the same way each time. For the most part, there are stochastic ways of doing modeling, but for the most part, they're just doing calculations that we tell them to. It knows nothing of its own context or its appropriate use cases. And we can fit some really accurate models, but when deployed to the real world, these golems, these statistical models, can break things, can have a very negative impact, and that could be due to overfitting, bias in the data, etc. Kind of something that's very important to know, though, is like we will eventually destroy Prague. That's what the golem of Prague did accidentally. But hopefully, as we know more about statistics, we'll be able to notice that destruction and hopefully determine why our golem, our statistical model, went wrong. So, straight quote from the book that I'm basing kind of this presentation from is that scientists also make golems. Our golems rarely have physical form, but they too are often made of clay, living in silicon as computer code. These golems are scientific models, but these golems have real effects on the world. So through the predictions they make and the intuitions they challenge or inspire, a concern with truth lives these models, but just like a golem or a modern robot, scientific models are neither true nor false, neither prophets or charlatans. Rather, they are constructs engineered for some purpose. These constructs are incredibly powerful, dutifully conducting their program calculations. So always remember when using statistics, machine learning, whatever, be mindful of what you're doing. And that will kind of lead us into this idea of small and large worlds. So worlds of different sizes. Small world is a ride at Disneyland, but in the sense of Bayesian statistics or statistics in general, this is like a self-contained logical world of the model. Its purpose is to verify a model's logic. It performs as expected, and hopefully is an accurate description of the real world or large world where we're going to deploy this model. And so the large world, like I said, is the area in which one deploys the model. And we hope that the small world on which the model was based on is a fair representation of the large world. And so Bayesian statistics is looking at all the combinations of the way that data can occur. And the more ways that that data can occur, the more plausible it is. And our aim is to use data as evidence to construct our model in the small world in order to best mimic the large world. So Bayesian statistics, I guess I'll explain this chart on the left after I kind of go through everything on the right. So in Bayesian statistics, there's not really an idea of minimum number of observations, and that's due to having priors and posteriors. A prior is just a certain belief about how the data looks or acts or whatever. A great explanation of this is like the normal distribution. It has a mean and a standard deviation, those parameters. And so you can update those parameters. So like, let's say at 0.1, we think that the mean is 0.5. We get some new data and we update, we adjust our belief and we move it maybe to the right, maybe to the left. And same with the standard deviation. And so we update at each new introduction of data. And the distribution of the posterior kind of reinforces that idea of no minimum sample size. The more confident that you are, the less uncertainty you have about your data, kind of the higher peak that a distribution will take on. And the shape of the distribution, how it like kind of comes out and embodies the sample size. There's no point estimates such as, mean, median, mode. They are useful, but the whole distribution is the estimate. And there's not going to be one true interval like we think of with normal statistic. So on the left, we have this chart that's like gradually updating over time with the green bar, the green line having a stronger prior at update 1, at increment 1, and the blue bell curve having a flatter prior, like less information preloaded into the system. And then as the updates go on, we can see how priming our system, priming our model with different informations beforehand can severely impact how we're going to update our beliefs. Any questions so far? I'll take silence as a no, so it's also okay. Sweet, so we'll keep chugging along. The garden of forking data. So we're gonna have this example of like tossing a globe. Imagine we have a globe, 25% of it's covered by water, and we can kind of see this depicted in this image to the right. It shows us what 3 tosses of the globe, what all the possible combinations and outcomes are. So, right, the blue one would be water, and then 3 blank ones would be land. And you can see kind of how that grows out and increases in size with each iteration. And we can take that and we can deduce plausibility depending on the probability that we believe about this globe. So things that occur in more such different ways are more plausible to occur. So imagine we throw this globe and it's water. We throw it again, it's water again, we throw it, and then it's land. And we can kind of see the plausibility of that. So for no land, we see that the probability of water is 0, and the ways to produce this specific combination is 0. Therefore, the plausibility is 0. And so we can calculate out the rest of the plausibility. So like 15% for this, 40% for 2, 45% for this. And because we saw land, it's 0% for all water. And so now we're going to move on to a code demo, or building the model as I'll call it. Whoops. Let's see if I can quickly switch over to code demo. And live keeps switching to the wrong screen. There we go. So I'll try to adjust my font size. Does anybody have a problem seeing it as is?
I can read it okay where I'm at right now.
Sweet. So I'm inside a Jupyter notebook. I know that engineers and I still cringe at Jupyter notebooks and like the bad quality of code that gets put into them, but we're just gonna have to live with that for now. But we're gonna, as we go through this, we'll kind of cover the topic of like how introducing new data over time affects things and kind of why it's powerful. So we can look at the different probabilities for different proportions of water to land ratios via generative modeling. Generative modeling means that we're going to like generate the data in a way that we believe it could exist. And so we're going to write out our own sample at first with, I think, 6 waters and 3 lands. And we're going to calculate all this probability stuff. This is just a quick way of calculating the number of combinations. It's a binomial formula, which we won't get too into the weeds about. Just know that it's like N choose C type of thing. And then determine the proportion each way that it could appear, and we'll get this output. So for this sample, for 6 waters and 3 lands, for the probabilities of 0% water, 25% water, 50% water, 75% water, 100% water for those proportions on this globe, the ways that we can end up seeing this, or the probability that the globe is 25% covered by water, is about 2.2%. 50% covered by water is about 40%, 75% water, it's about 58%. And so you can start to see like, oh, you know, like perhaps we added another toss in there. It might take a while because I haven't reloaded this library, but we can see how that drastically changes the outcome probabilities. So as we keep going, like now we'll write this simulate globe function, which is a generative simulation for tossing this globe, where P is the proportion covered by water and it equals the number of tosses. We'll code this estimator and compute the posterior, which is on the same table that we saw above. We'll hand in our sample, we'll hand in a list of possibilities that we want to look at for the probable toss. And we can see that for this, a random sample of 15 with a proportion of 70%, like these are our probabilities. So looks like 6% for 50%, and then 94% for 75% covered by water. And we can kind of take this and keep growing this idea out, where now we're going to sample from the posterior and graph the density function. So this data comes from like a beta distribution for one reason or another. That's what it will end up mimicking. And then we'll plot the kernel density estimate of it to see like how the data looks. And then we'll actually grab a bunch of samples to plot, or sorry, we'll grab a bunch of samples from the posterior to plot on top. So this is generating the globe tosses, and this is generating the actual density, the actual distribution that we're trying to mimic. And so when we run both of those things, we can see like our artificial tosses strongly mimic this beta distribution. And so our posterior distribution, what we're aiming to kind of estimate, is this black dashed line. And so this is where it kind of starts to become powerful, in the sense of we no longer need to keep track of all the previous tosses. We can store this information at in subparameters, so like maybe an alpha and beta variable parameter, I guess, for a beta distribution. I don't want to get into the nitty gritty of like what a beta distribution truly means, but the parameters, alpha is like the number of successes plus 1, and beta is the number of failures plus 1. And that will kind of generate this curve. And so we can look at different ways of understanding priors with this kind of code that's going on. So we're going to create this linear space of the first curve that's just initiated with our uninformative prior, flat prior. We just don't feed our model any data. And then we have tosses. We'll grab 9 tosses, and then we'll kind of move through each toss. And we'll run this real quick just because I need to reset it with the uninformative prior of alpha equals 1, beta equals 1. And we can see that like our posterior distribution really isn't that confident in any values outside of the middle. But as we add another iteration, so now we've tossed the globe, and it probably came back water. Now we're starting to shift to the right. We start to see this peak kind of increase. And then we toss it again, we toss it again, we toss it again, we toss it again, we toss it again. This will eventually start to peak around that 0.7, 0.8, which is where the true mean lies. What's very interesting about this curve is that it contains our uncertainty about what we believe about this globe toss, about the true proportion of water on the globe. And if I scroll back up enough, we can see that we didn't have to use the calculation, converting the W's and L's into 1s and 0s each time to create these numeric values. Instead, we were able to store the toss into a single value for each one, an alpha and beta. And that's very, very cool to me because now you've kind of segmented your way out of having to retrain a model on the entire data set each time. You can just incrementally add new observations as they come in and to update your parameters. So we'll come down here back to the posterior predictive. So now that we know that like, oh, it's like we're starting to build this posterior distribution and it's starting to line up with what we know the true proportion of water is, which is around 70%. We want to say, you know, what's the likelihood of tossing a globe 9 times and getting less than 7 waters in that toss? And we can do that. So we'll go back to the sample of 6 waters and 3 lands. We'll generate that data again when 10,000 tosses. And then we'll do this thing where we throw the globe and look at the predicted posterior, which is the number of times that water was seen. And then we're going to tabulate results and then plot things below. So when we run this, we see that we have this belief about 65% of the tosses are going to be water, and then we can see the number of waters that are likely to occur for 10 tosses, and we can change that. Like, let's say we wanted to toss it 100 times, and that's not going to plot it because I have done this incorrectly, but this is why you don't do live code demos. I just have my plot set up to go from 0 to 10, I think. But yeah, you can start to look at like what's the likelihood of doing 7 or less tosses, 4 less tosses, 8 or more tosses, and getting water back. So you want to use the posterior predictive distribution to kind of pull probabilities and likelihoods out of, just for the sake of converting our beliefs into uncertainty and truly getting out predictions instead of having these kind of weird abstract distributions that may or may not be correlated with other things that you're training at the same time. So we'll go back to the slides. And so, yeah, so we'll start to analyze output, but are there any questions about that code demo I just ran through? Sweet. So, there we go. Bayesian inference. So there's, like I said before, there's no minimum sample size. N of 1 is not very accurate, but that's by design, right? We have built uncertainty into our model, and the shape of how of those curves look embodies the sample size. So sample size is not an extra number that needs to be carried around. Instead, you could just look at your posterior distribution to gain that information, that understanding about uncertainty and confidence. And then you can always let your posteriors that after you've looked at data and use that as your prior for the next time. There's no point estimate. So think of the whole distribution. That's the estimate. You can use some summary points and summary data, but the whole distribution is what's going to really help you learn and make estimates and predictions about your data. When we compute from the posterior distribution, we need to use the whole distribution, not just single parts of it. And that goes back to the whole distribution contains all that uncertainty, contains all that data that we've wanted to use. And then no one true samples, true interval. That's merely a summary of the distribution. A lot of people will talk about like 95% confidence intervals or prediction intervals or whatever. Those are just arbitrary locations that give you understanding about kind of the shape of a distribution. But that's largely it for this kind of first section. And I could stop here, or I could kind of jump into another code demo that kind of extends this to the linear regression with Bayesian modeling, if that's interesting to anyone.
Everybody throw a thumbs up for the next one, or what? Well, we got a thumbs up.
Well, I guess, yeah, we'll go into the next code demo. So that first section was largely about priming our understanding about how distributions start to work, how we need to sample data, create generative distributions, but it is not exactly linear modeling, right? Like how is that done type of thing. And so we can hop into this really long code demo, but it will be good. I'll run this real quick. So we're going to look at a data set that contains information about weight, height, age, and sex for different individuals. For now, though, in this specific code demo, we'll just look at how height affects weight and how we can model that with a Bayesian linear regression. So one of the first things that we'll do, obviously, is load up the data, and then we'll create some scatter plots as well as put the head of the data. For the sake of this, we're just going to look at adult. Excuse me. I'm sorry. We're going to look at the data for those individuals that have a height or an age greater than 18. So we're just going to look at adults. The reason for that is like there's this really weird burn-in curve for children that can be modeled with Bayesian linear regression, but we're just not going to focus on that right now. That's a bit more nuanced. So the first thing that we need to do is create a causal or scientific model about what we believe about the data. So how does height influence weight? And so, weight is some function of height. The taller that you get, the more weight you are likely to have, but it's not necessarily the other way around, right? Like the heavier that you are, the higher, you're not going to get taller. You can gain and lose weight, and that's not going to affect your height necessarily. So now we're going to generate a function to generate our simulated data. And this is kind of creating a small world, that idea of prepping ourselves to generate a model that will mimic the big world. And the purpose behind that is we don't want to immediately just jump in with real data that will affect and bias how we generate a model and how we come up with our analysis and our outcomes. So we're going to create some function with height as a parameter, then some unobserved stuff that also affects weight. And then we can define this linear regression as weight equals beta times height plus the unobserved, where beta is the slope value. So for each increase in h, we'll see the beta value increase in weight. But for our generative model, we'll have weight be distributionally defined as some function of beta times height plus unobserved, where unobserved follows a normal distribution with a mean of 0 and some standard deviation sigma. And then height is uniform from 130 centimeters to 170 centimeters. And these are just kind of random values that we will end up kind of tweaking in a sense later on, but we'll get there when we get there. So for now, we'll just simulate these weights by writing all of that pseudocode into actual code. And then we can plot it and we can see like, oh, hey, yeah, like the frequency is kind of jumbled, but, largely uniform. And it really does mimic that data that we saw up above. So now we want to estimate how the average weight changes with a given change in height. So the expected value of weight given height equals some alpha plus beta times height. And we can talk about this posterior distribution, but I'm going to skip over it for now. I don't think that it's necessarily useful to dive into the theoretical mathematics at this point. But what will be helpful is kind of trying to visualize an example of how we're updating these lines. And this isn't going to be based off of the height weight data set that I was showing above, but this is just like random values. So on the left-hand side, we can see like we have an intercept defined on the x-axis and the slope defined on the y-axis. And we're just going to start like throwing random guesses out there. So we'll pull 3 random samples from our posterior distribution where n equals 0, so we have no data. And we can see that these lines are kind of all over the place, with the dotted line and the x being the true parameters. As we start to increase the amount of data that we have into our model, just kind of stepping through it, incrementally adding data, not necessarily refreshing the model each time, we can see that these dots are starting to kind of come closer to the true value, the true trend. And as this data keeps increasing, we can see that the probability starts to focus closer to the x, closer to the true trend. As we get down to n equals 64, we can see it's basically right on top of that point, and right on top of that true trend. And that's a really cool feature of posterior distributions Bayesian statistics. Like we can always update our belief about where the intercept and the slope is. Whereas with frequent statistics, you have to rerun the model each time instead of just introducing a single new data point. So now we need to validate our model that we kind of described up above. And we should express our knowledge softly. When height is 0, weight should probably be 0. On average, weight increases with height, and weight should normally be less than height. And variance is a positive value, and that's just a statistics thing. You could use a uniform distribution. You could use the half normal distribution. Just really anything that allows you to be like, our standard deviation is above 0. And alpha is that intercept, so height equals 0, and we have this belief like normal with a 0, and then there's a variance of 10. That's a very flat prior, it's very wide. And beta, so for each increase in height, we expect no increase in weight, but there's a variance of 1, so like there could be some upward or downward shift. Again, it's a very uninformative prior. And priors are sometimes important, they are not always important. So in this example, not too important. Our model isn't that complex. So our parameters, our posterior, can adjust rather quickly. Whereas for a more complex model, the better that we can prime our data, our model rather, the quicker it can kind of converge to the true values. And so we can do like a simulation, make up a bunch of heights, and when we sample and we look at a random sampling of like 20 or so lines, they're kind of all over the place. We don't really have a belief about them. And so now we want to simulate and validate our data, our generative model, and validate what we think the true model should be. And so when we do that, like Bayesian statistics is all about like this MCMC, Markov chain Monte Carlo sampling, where you just like sample a bunch of times and it will get you closer and closer to the true parameters. And so we'll print out sample size, which I think will be different ones So 1, 2, 10, 20, 50, and then the true length of the data that we will eventually feed in. And we'll have mutable data. So this just defines this H underscore variable for the rest of this model session, model scope. And then we'll have our priors set here. So some noise variance for sigma for what weights should be alpha. So like the intercept where height is 0, like what we believe weight should be, and then our slope beta. These are all primed with really uninformative and incorrect parameters. And so when we run this and we get our inference and we append like models and inferences and stuff, different lists, we can see how they end up performing. And I think that will be down here. So this is just a lot of stuff to plot these graphs. So with a sample size of 1, we can see that the model are all these lines. The darker the line, the more probable the posterior distribution is. The more probable this linear regression is. And we can see that like with an n equal 1, a sample size of 1, it's rather uncertain. But by the time we get 200 samples, we've like really honed in on a linear, on a good Bayesian linear regression. And this is all off of simulated data. And so now that we've validated our generative model, we validated our scientific and causal model, we can jump into analyzing the real data. And so when we pass that in, we can get out a bunch of summary statistics about the inference and stuff. We can get a bunch of metadata about the different parameters. But the cool part is like we can see that n equals 352. So I guess I truncated some values out up above, but we can see that the true Bayesian linear regression ends up really following that data. And we can, I haven't run any of this code, and it will take a while to run because of the sampling, but it's really interesting because you can always update those models as they come through. And that's like the true power of Bayesian statistics, and something that I'm actually actively working on right now is longitudinal analysis with Bayesian methods, and to try to kind of lower our cloud cost spend. So using like Bayesian modeling, we're able to iterate at each check-in point for a study that we're doing, and then refocus our parameters. And we'll never like have this weird problem where like the model output's always shifting left and right with different p-values, but we can see it kind of hone into the true parameters and true likelihood of a study. So
I have a question.
Yeah.
Just change my question. Okay, yeah. So you had mentioned you can add, was it just like new parameters, like a new type of parameter on the fly, or was it just the data points you can add on the fly without having to bounce around?
Yeah, so it's typically new data points on the fly that you can add. But having said that, you can extract the posterior parameters for like the statistical modeling that you're doing, and then feed that into a new model as your priors for that new model. So if you had this model, we're training it over time, and you decided, what, there's this additional feature that we would like to add, but we don't want to really spend all this time retraining on all this previous data. You can kind of bring that back down, do some analysis to pull out those parameters for like the normal distribution, the sigma, the alpha, whatever, and then feed that back into the model and keep growing from there.
So yeah, okay, essentially you extract it from the posteriors, link it to the priors, and off you go with your new. That's pretty cool.
Yeah. So lots of fun use cases. Something that I've done in the past is do like anomaly detection for a fintech company that I was working with, in terms of like, is a user going to overspend on a budget this month? And then, what a proper budget should be. Typically, as time goes on, prices increase. And so we should always try to be like moving and matching like the true spend that a person has. but not like over adjusting. And so that these processes worked really well for that without ever having to kind of need to spend a bunch of time running it for every single user, because you could just create a generalized case and use that prior for, you know, different clusters of users, and then gradually run those models ongoing for them, or whatever you may want to do.
So
I have a
another
question.
question on that. Oh, go ahead. No, I've already asked a question. You take a turn.
No, I'd love to know, Stephen, where do you think Bayesian testing breaks down? Right. So obviously every tool is useful within a certain class of problems to solve. Where in your experience do you find Bayesian testing breaking down? And I'm guessing it's probably in some of the assumptions of the underlying models that you make, that it would probably be really tough. And I'm just wondering, how sensitive is it? Like if you assume, you know, a static system versus something that truly is dynamic, I imagine that would probably mess some things up. What are some of the patterns that you see when you're starting to use this, where it's like, oh my gosh, this is wrong, my assumptions are wrong, this isn't working out well? I'd just like to know the limits on it.
Yeah, I feel like, you know, you're going to run into the same limit as frequentist statistics, as well as like buy-in from those with less statistical knowledge or mathematical foundation. That being said, though, a recent example is I was doing this Bayesian analysis for an A/B test, and I had used the prior for data that was probably 1 or 2 orders of magnitude larger than the data that I was analyzing. And it just kind of failed there. I saw really funky outputs. I would look at my distributions, my burn-in, or that's not, I'll use a less technical term, but like as the model was training, I never saw it truly converge to a true point. It was very wonky in its output distributions and posterior distributions. And so it can break down rather quickly if you're trying to do something more complex and might not have the best domain knowledge about where your prior should truly lie.
So it is sensitive to prior assumptions, not necessarily prior initializations, is what you're saying. So if you can probably initialize your priors to whatever you want it to be, but your prior assumptions themselves, the relationships of your priors, has to be fairly solid. Is that what you're saying?
Yes and yes. So yeah, so your priors, it depends on how accurate they need to be, depending on the complexity of the model, and that's just due to kind of like the I'll say learning rate, for lack of a better term currently, learning rate of how these parameters adjust. Another place where it can break down is if you don't correctly define your scientific model, if there are causal influences that are spread out across multiple other features and you don't properly spec that into your model, then you can run into issues with achieving convergence in your sampling and determining those parameters for those internal distributions.
Thanks.
So just on the question I had was for the example you gave on doing like cloud cost analysis, like what were some of the examples of what your parameter selections were for that? Like was it like
Parameter
resource
selection.
types? Yeah, like
Oh, sorry. Yeah, so it wasn't necessarily, so I was doing A/B testing to try to bring down cloud cost, not necessarily to analyze cloud cost. Sorry for that
Oh, I see.
miscommunication.
Okay.
Yeah.
So in other words, it'd be like a setup of something, run it, tear down, setup of another thing, run it, and you would be able to make assumptions based on those things you measured.
Yes, I think so, if I'm understanding you correctly. Yeah.
Okay. Yeah. Versus just going out in the wild, looking at your cloud and saying, let's just look at this and find all things that could be tuned. You were like kind of focused on a setup and test of a isolated scenario versus another one.
Yep. Yes. Yep.
Yeah, that makes sense.
Cool. I don't think that there probably will be other questions, but I guess I can hand it back to you, Pat.
Yeah, did anybody else have anything else?
I'll ask one more, if you
Yep.
don't mind. So you mentioned A/B testing. That's kind of the world I live in. One of the biggest problems we find in A/B testing is you launch a test and literally you have executives that want to know 2 minutes later what's doing better, right? One of the benefits I think of doing Bayesian reasoning would seem to be that your models can take into account small sample sizes, but it seems to be the exact same weakness you see in frequentist models, which is it takes a while for you to get significance. It seems like maybe you can confirm or deny. It seems like you're not really gaining much in using a Bayesian reasoning model versus a frequentist model because it still comes out in the wash as either extra uncertainty. You have to basically play with your confidence intervals in a frequentist model versus in a Bayesian model, you have to get enough samples for when things converge. Maybe you can help me understand, what's the upside of using Bayesian versus frequentist, or are they basically equally as powerful? You're just making trade-offs in terms of confidence interval because it still has the same problem as you communicate up to executives, wait a couple more hours before we call it, right? Wait a little while
Yep.
before we actually, if your model doesn't have enough information, it doesn't matter whether you're using frequentist or Bayesian to be able to solve it, you still have the same problem.
So yeah, that's a great question. I definitely land in the camp that Bayesian statistics is more powerful. And the reason for that kind of comes down to the interpretability differences between frequentist and Bayesian statistics. With frequentist statistics, your model often follows a kind of definition of y equals alpha, so your intercept plus beta times feature one, and then you have as many features as you want, as many categorical adjustments as you want, plus some unknown error factor. And so when interpreting more frequentist statistics, you aren't able to push out posteriors, not able to post out predictive distributions. And the weakness there lies with like the idea of a confidence interval, where a confidence interval is saying, 90, I have a 90% confidence interval, but that boils down to is like 9 times out of 10, if I run this test, I'll have this value in this 90% confidence interval range. It's not saying I have 90% probability that the true value lies in this range. That's not what a confidence interval means at all. And I think that's a very large drawback. Whereas with Bayesian statistics, you say I have a 90% credible interval where there's a 90% probability that the true value for this parameter, for this feature impact lies within this area. And so you gain a lot there. And so even if you have like a sample size equal to 1 for frequentist statistics or a sample size equal to 1 for Bayesian statistics, there's a lot of power that comes with that. Whereas with frequentist statistics, you're saying like, I really don't know anything about these like huge margins. I can't really interpret anything from this. With Bayesian statistics, you have a prior loaded in there with information, hopefully, from more knowledgeable domain users or experts, domain experts. And so with that information preloaded, you can more quickly derive the true parameters, even though there's extra uncertainty there still. You're more likely to be in the correct realm of possibilities.
Okay.
So would it be fair to say that you don't have the peaking problem when you do a Bayesian analysis or regression? I'm not sure what you call it versus the statistical regression.
Yes. Yep. Yeah. You completely avoid the peaking problem with Bayesian statistics and regression that you would find with frequentist statistics.
Okay, sounds like that's everything, right?
Yeah, good for me.
All right, well, thank you, everybody. I really appreciate everybody coming. And Stephen, thank you for the presentation. Really enjoyed it. Hope everybody got something great out of it. We'll go ahead and stop our recording now.